Welcome back to the channel. Today, we are going to tackle one of the most misunderstood concepts in the entire networking landscape. We are talking about BGP, but not the BGP you usually hear about in the news when the internet breaks. We aren't talking about peering with an ISP or connecting two different companies. We are going deep into iBGP, Internal Border Gateway Protocol. If you are studying for your CCNP Enterprise or service provider exams, or if you are an engineer stepping into a large-scale enterprise or data center role, this is a make or break topic. Here is the hook, and here is why this matters. Most engineers think of BGP as an external protocol. It's in the name, Border Gateway. So a common question arises. If I already have OSPF, EIGRP, or ISIS running inside my network to handle routing, why on earth would I complicate my life by running BGP inside my own autonomous system? The answer lies in scalability, policy control, and the fundamental architecture of modern networks like MPLS VPNs and SD-WAN. In this deep dive, we are going to strip away the confusion. We are going to look at the architecture of iBGP, the notorious split horizon rule, the full mesh requirement, and how we actually solve that in the real world using route reflectors. We will also cover the critical differences in next hop behavior that trip up almost every engineer the first time they configure this. Buckle up, let's get into the terminal mindset. Section 1, the architecture, iBGP versus IGP. Let's start by establishing the ground rules. What defines iBGP? Technically, BGP is BGP. The packet format is the same, the finite state machine is the same, the difference is purely administrative. When you form a BGP neighbor relationship with a router that shares the same autonomous system number as you, that is iBGP. If the AS numbers differ, it's eBGP. Simple enough, right? But the behavior changes drastically. To understand iBGP, you have to understand the separation of duties. In a carrier-grade or large enterprise network, your interior gateway protocol, your OSPF or ISIS, has one job: loopback reachability. That's it. We want the IGP to be lean, mean, and fast. We do not want to dump 900,000 internet routes into OSPF. OSPF implies that every router has an identical database. If you try to push the global routing table into OSPF, your router's CPUs will melt and your convergence time will be measured in minutes, not milliseconds. This is where iBGP comes in. We use the IGP to build the highway, the infrastructure. We use iBGP to drive the cars, the actual customer data or internet prefixes over that highway. iBGP allows us to transport massive amounts of routing data across our transit backbone without every single router in the middle needing to do heavy calculations. It also allows us to carry rich attributes, local preference, communities, MED, across our internal network to influence how traffic enters and leaves our AS. You cannot do that with OSPF. So the first mental shift you need to make is this. iBGP is not a replacement for OSPF. It is an overlay that relies on OSPF to function. Section 2. The Loop Prevention Mechanism, Split Horizon. Now let's get into the deep technical weeds. This is the part that shows up on the exams and the part that causes outages if you don't respect it. In eBGP, external, loop prevention is easy. We use the AS_path attribute. If I receive a route update and I see my own AS number in the path, I drop it. It's a loop. But think about iBGP. We are inside the same AS. When I send a route to my internal neighbor, I do not prepend my AS number because we are in the same AS. If I did, the neighbor would reject it. So the AS path attribute does not change as an update moves from router to router within an AS. So how do we prevent loops? BGP developers came up with a very strict rule known as the iBGP split horizon rule. The rule states a router functioning as an iBGP speaker cannot advertise a route learned from one iBGP neighbor to another iBGP neighbor. Let me repeat that because it is the most critical constraint in iBGP design. If router A tells router B about a network, router B accepts it. But router B is strictly forbidden from passing that information on to router C if router C is also an internal neighbor. Why? Because without the AS underscore path changing, router B has no way to know if router C has already seen that update. To be safe, BGP simply forbids the propagation of internal updates. Section 3. The full mesh requirement and scalability. This split horizon rule creates a massive architectural problem. Imagine you have a network with routers A, B, C, and D in a line. A tells B. B knows the route. But because of split horizon, B cannot tell C, and C definitely can't tell D. The result? You have a black hole in your network. Traffic enters, hits a router that doesn't have the route, and is dropped. To fix this, the default requirement for iBGP is a full mesh. Every single router running BGP within your AS must peer directly with every other router running BGP. If router A peers directly with B, C, and D, it can send the update to all of them simultaneously. Since they all receive it directly from the source, router A, no one has to repeat it, and the split horizon rule is satisfied. But let's look at the math, because this is where the deep dive aspect comes in. The formula for a full mesh is n times n-1 divided by 2. If you have 4 routers, that's 6 connections, manageable. If you have 10 routers, that's 45 connections. If you have 100 routers, that is 4,950 BGP sessions. That is administratively impossible. You cannot configure, maintain, and troubleshoot 5,000 TCP sessions on your devices. The control plane overhead would be astronomical. So while the full mesh is the theoretical requirement to satisfy split horizon, nobody does this in production for large networks. So how do we cheat the rule? Section 4. Breaking the rules. Route reflectors. We solve the full mesh scalability issue using route reflectors, RR. A route reflector is a BGP feature that allows us to deliberately break the split horizon rule in a controlled manner. Here is how it works. You designate a specific router as the route reflector. The other routers become its clients. When a route reflector receives an iBGP update from a client, it is allowed to reflect that update to its other clients and non-clients. It acts as a central hub. Now, instead of a full mesh where everyone talks to everyone, all routers just peer with the route reflector. If you have 100 routers, you don't need 4,950 sessions. You need 99 sessions pointing to the RR. However, because we are breaking the loop prevention rule, split horizon, we need new mechanisms to prevent loops, because we've just reintroduced the possibility of a loop. When you enable route reflection, BGP adds 2 new attributes to the update. 1. Originator ID. This is the router ID of the router that originally injected the route into the iBGP mesh. If a router receives an update with its own originator ID, it ignores it. 2. Cluster_list. This tracks the route reflectors the update has passed through. It works exactly like an AS path, but inside the AS. If a route reflector sees its own cluster ID in the list, it discards the update. For the CCNP exam and real-world design, you need to know the reflection rules. If a route is received from a non-client, like an eBGP peer or a standard iBGP peer, the RR reflects it to all clients. If a route is received from a client, the RR reflects it to all non-clients and other clients. If a route is received from an eBGP peer, it reflects to everyone. This design pattern is the standard for service provider networks and large enterprises. We usually deploy route reflectors in pairs for redundancy so that if one goes down, the entire routing table isn't lost. Section 5. Next hop behavior and next hop self. Now that we have solved the propagation issue, we run into the connectivity issue. This is the second most common problem engineers face with iBGP. Let's visualize a scenario. You have an edge router, router A, connected to an ISP via eBGP. You have an internal core router, router B, running iBGP with router A. The ISP sends a route to router A. The next hop IP address for that route is the ISP's interface IP. Let's say 1.1.1.1. Router A advertises this route to router B via iBGP. Here is the catch. By default, iBGP does not change the next hop attribute. Router B receives the update. It looks at the route and sees the next hop is 1.1.1.1. Router B then looks at its routing table and asks, "Do I know how to get to 1.1.1.1? Usually the answer is no. That 1.1.1.1 address belongs to the ISP. It is not in your OSPF or EIGRP internal routing table. So router B marks the route as valid but inaccessible. It will not install it in the routing table and traffic will fail. There are two ways to fix this. Method 1. You redistribute your connected external links into your IGP. Do not do this. It is bad security practice and bloats your IGP. Method 2. The correct way. On router A, the edge, you configure the command neighbor router B next hop self. This tells router A, when you send this route to router B, take off the ISP's IP address and put your own interface IP, usually your loopback, as the next hop. Since router B already knows how to reach router A's loopback via OSPF, the route becomes valid, the recursion succeeds, and traffic flows. This is a mandatory configuration in almost every iBGP deployment. Section 6. Comparing iBGP to IGP and EBGP. Let's take a moment to compare these protocols to solidify your understanding. Performance and convergence. IGPs, OSPF/EIGRP, are designed for speed. They detect failures and reconverge in milliseconds. iBGP is slower. It is designed for stability. We do not want the global internet table flapping every time a link jitters. iBGP timers are slower by default, and the scanning process for the BGP table takes longer because of its size. Administrative distance. This is a key differentiator. eBGP has an administrative distance, AD, of 20. It is very trusted. OSPF has an AD of 110. iBGP has an AD of 200. Why is iBGP so untrusted? Because we assume that if a route is generated inside our own AS via an IGP, it is likely more accurate regarding the topology than a BGP route bouncing around internally. This prevents iBGP from overriding your internal infrastructure routes. Attributes. In eBGP, we manipulate paths using AS_path prepending and MED. In iBGP, the king is local preference. Local preference is an attribute that only leaves the router to go to iBGP neighbors. It is stripped when leaving the AS. It is the primary tool we use to tell all routers in our AS, exit the network this way. Section 7. Real-world scenario, MPLS Layer 3 VPNs. Let's look at the ultimate use case for iBGP. Why do we go through all this trouble? Consider a service provider offering MPLS Layer 3 VPN services to customers. Customer A has an office in New York and an office in London. They want them to talk privately. The service provider has a massive backbone. We run OSPF in the core just to get the provider routers talking. Then we run MPLS. Finally, we run multi-protocol iBGP, MP-iBGP, between the provider edge routers. We do not run iBGP on every router in the core, the P routers. We only run it on the edges and use route reflectors. When customer A sends a packet in New York, the PE router wraps it in an MPLS label and sends it across the core. The core routers, P routers, have no idea who customer A is. They don't have the customer's routes. They only know how to switch the MPLS label to get to the remote PE router in London. iBGP is the protocol carrying the customer's routes and the associated VPN labels from New York to London. OSPF provides the reachability for the tunnel endpoints, and iBGP carries the payload data instructions. Without iBGP, you cannot build a modern MPLS or SD-WAN network. It is the control plane that allows you to virtually slice your network into thousands of private segments. Section 8, Summary and Key Takeaways. We have covered a lot of ground, so let's summarize the critical points for your deep dive. 1. Definition. iBGP is BGP peering within the same autonomous system. It is used to carry external prefixes and customer routes across a transit backbone. 2. Split horizon. The rule that prevents a router from advertising an iBGP-learned route to another iBGP neighbor. This prevents loops because AS_path is not modified inside the AS. 4. Full mesh. The theoretical requirement to overcome split horizon, which is mathematically impossible to scale. 5. Route reflectors. The practical solution. They break the split horizon rule to allow a hub and spoke propagation of routes, using originator_ID and cluster_list to prevent loops. 6. Next hop self. The mandatory configuration on edge routers to ensure that internal routers have a reachable next hop IP for external routes. 7. The hierarchy. Use IGPs, OSPF/ISIS, for infrastructure reachability, loopbacks and links. Use iBGP for the service layer, internet routes, VPNs. BGP is not just about connecting to the internet. It is the glue that holds large-scale internal networks together. Mastering the interaction between your IGP and iBGP, understanding the flow of attributes like local preference, and designing scalable route reflector hierarchies are the hallmarks of a senior network engineer. If you are labbing this up, and you should be, start with a simple 3-router ring. Watch the split horizon rule break your connectivity. Then configure a full mesh to fix it. Then tear it down and configure a route reflector. Use the show IP BGP command and look specifically at the next hop and cluster list fields. That is where the truth lies. Thanks for watching this deep dive. If you found this valuable, make sure to check out our other videos on MPLS and OSPF advanced configurations. Keep tracing those packets, and I'll see you in the next one.